In this session, I'm going to demonstrate the importance of probability sampling. Most specifically, I'm going to demonstrate why sample size matters and why we have to pay attention to both sample size and the conclusions one can draw from some type of survey or some type of sampling or some probability of an occurrence. Social scientists try to count many different things in society, whether it's population or certain kinds of behaviors, but we can't measure everybody. And so to draw conclusions about society or about our different populations or characteristics of the populations, we have to sample that population because we can't measure everybody. It's too expensive, it's too hard, we just can't do it. So we have to sample the population. And so to do a good sample, we have to have a well-defined population. It could be all women or all men or all voting age adults or all people that have red hair or all people that have a certain kind of illness or characteristic. No matter what, though, we have to define our population carefully. And then a good sample of the population is randomly drawn such that each person in that population has an equal chance of being selected. So from a pool of people or a pool of characteristics in the population, I have to randomly select among those folks so that everybody has an equal chance of being selected. I don't want to bias it so that I only select or I over-select a certain kind, or I underselect a certain kind of person or characteristic of my population. And lastly, my population and my sample, it has to be of sufficient size from which to draw meaningful conclusions relative to what I'm trying to measure. So what are some examples of sample-derived data? Well, the monthly unemployment rates nationally as well as for the 50 states, those rates are drawn from a continuous national survey of households. Annual poverty estimates are drawn, again, from a survey of the United States and the various states' households. Consumer spending characteristics and consumer confidence and other kinds of indexes. These are based on samples of the population. I've had presentations and sessions on the American Community Survey, most especially what the results contain as well as the kind of confidence we can have in those results. Again, the American Community Survey is a continuous random sample of U.S. households. Certainly, we're aware of public opinion polls. There are several companies, Roper, Gallup, PPP, Rasmussen. These are firms that make their living by drawing public opinion polls. Marketing research, of course, uses sampling of the population to figure out whether certain kinds of products are desirable or not. And then finally, and most important for us as society, we have to do good samples of the population or of certain types of phenomenon to conduct valid scientific research. So we're going to work through a very, very simple example. Suppose I had a deck of cards, and in that deck of cards there was 20 cards. There were 2 twos, 2 aces, 2 threes, all the way up through 2 tens. And aces we're going to count as 1, right? And I shuffle the cards, and I shuffle them well, so that introduces randomness. And then I'm going to deal you 2 cards, and you're going to add those 2 cards together. Now the big question is, what's the probability of my 2 cards adding to some number, be it 2, or 8, or 16, or 20? We can show the probabilities of a specific score by creating a matrix, and that's what I've done right here. Let's imagine that this is one set of cards, ace through 10, and here's another set of cards, ace through 10, and these represent all of the pairing possibilities. Well, how many ways can I get a 2? Well, the only way to get a 2 is to get 2 aces, or 1s in this case. How many ways can I get a 3? Well, I could get a 2 and a 1, or a 1 and a 2. so I can get 2 3s. And you can see the diagonal values here tell me how many possibilities there are for me to score a different score from the 2 cards. I randomly shuffle, I deal 2. I take the cards back, I randomly shuffle, I deal 2. How many ways can you get a 4? There are 3 ways to get a 4. How many ways can you get a 5? There are 4 ways that you can get a 5. And so on and so on and so on until I find out that there are 10 ways that I can score 11, given all of these combinations. And then the probabilities start to reduce. Fewer ways to get a 12, even fewer ways to get 14, fewer ways to get 17, fewer ways to get 18, and then finally there's only one way to get a 20, and that's to be dealt 2 10s. Well, from that table we can plot the probability, the actual odds from that table of receiving a specific score. It's a 1% chance of me being dealt 2 cards that would sum to add to 2. And on the other end, there's a 1% chance of me being dealt 2 10s so that the sum equaled 20. There is, however, a much higher chance, a 10% chance, that the 2 cards that I'm dealt will equal 11, a 9% chance that the 2 cards will equal a 10 or a 12. So you see what we have here. We have much higher chances of these scores, much lower chances of these scores, and very low chances of these scores. The problem is that randomness and sample size may not produce exactly that perfect distribution that we just saw. Too small of a sample size may underrepresent or misrepresent the population to be analyzed. Too big of a sample size, and this gets into sampling theory, is expensive and inefficient. What we need is a sample size that is sufficiently large to produce a reasonable distribution of what I'm trying to measure. And so the trick is balancing our risk of sampling error, meaning I just made minor mistakes in choosing my population, as well as the variability in my population. I need to balance those risks and that variability against my information needs. Here is a distribution of the actual probabilities and a set of sample results from, imagine this, I dealt the cards 1,000 times. So there were 1,000 occurrences, 1,000 chances to get the scores of ranging from 2 to 20. And I did this, I'm doing this with a spreadsheet, but just imagine that I did this 1,000 times. 1,000 times I dealt you 2 cards. We wrote down the score when we added them together. You gave me the cards back. I shuffled them well, and I dealt you 2 cards, and again, and we repeated that 1,000 times. Well, I can simulate doing this 1,000 times very easily with a computer. But now let's just imagine that this 1,000 times that I did this represented 1,000 doors that I knocked on to try to obtain some information from a population that ranged from, it had 20 categories from 2 to 20, and where most people were within the categories of 8 through 15, and relatively few people were 2 through 5, let's say, or 17 through 20. And I'm knocking on doors and I want to get these scores. I'm going to do that, and I'm going to do that 1,000 times. How might my sample vary every time I tried to conduct a sample of 1,000? Well, this distribution right here, this was the first one, it looks pretty reasonable. It's similar. It's a little bit underrepresented. The blue are the actual odds. The red are the sample results. I'm a little bit underrepresented here in the 4 and the 5 category. I'm slightly underrepresented in the 2 category, but I'm a little bit over in a few others. Let's do it again now. Now I get a new distribution, and you can see the red bars have changed. The red bars have changed quite a bit in some instances. I seem to be underrepresenting these folks and overrepresenting these folks, or these scores, or these numbers, or these characteristics of the population. Let's do it again. And see, we get another situation where I have a much higher representation of this score and slightly lower representations, let's say, of these scores. Let's do it again. Every time I draw this sample, every time I conduct this survey, every time I attempted to measure this population, I ended up with differences in my results. Look at this example. I've got many fewer 9s than would have been expected. I've got more 11s than would have been expected. I have many more 14s than would have been expected. So you see what happens when we conduct a sample, given the actual odds and what we get out of our sample. We get a lot of variability. Now I have a sample size here that's 1,000. That's a pretty big sample size. Let's do this just a few more times. There's one that looks pretty close, except it's pretty underrepresented on the lower end. One more time. Here's one that, again, looks pretty close. We're going to do one more, and one more, and one more. And you can see that every time I draw a sample, it may look relatively close, like this one does, although there are variances, or it might be skewed quite a bit in one direction or another. Now I've reduced my sample size to 200. That's all. I'm just sampling 200, whether it's 200 households or 200 pigs or 200 trees or 200 of something out of a large population. And I have a known distribution. Those are the values that are in the blue. And then I have the results from my sample. And you can see on this first sample, I get many, many more 12s, many fewer proportionately 8s. And you can see that the error is much greater than we saw when we were drawing a sample of 1,000. Now I'm going to go through this and we're just going to look at how the results vary as I go through different iterations. Here's the second one. Here's the third one. Here's the fourth one. This one is quite skewed in the middle, very underrepresented across a couple of categories. Very overrepresented in the 15 and 16. Here's another one. Here's another one. Not as bad perhaps as some of the others, although there is overrepresentation of the 12 and the 7. Here's another one, and here's another one. So you see, the sample size really does matter. You get wildly different results with a small sample size versus when we had the larger sample size of 1,000, where the results more often than not were relatively close to the actual probabilities. So what we can conclude from this is that the sample size does matter. We have to have a sample of sufficient size to be able to draw reasonable conclusions about the population. In the example I just showed, 200 is too small, though you may see many surveys that only surveyed 100 to 150 or maybe 200 people. And then the results of those surveys are represented as indicative of the population that was surveyed. And from the results that I just showed you, that very well might not be the case. As a matter of fact, it's likely not the case that a survey that's that small could possibly represent the characteristics of a population.